I will be introducing a efficient implementation of a new algorithm proposed by Joux-Vitse in 2017. As most of you already know, MQ and P system can be used to construct post-quantum cryptographic systems. And there are encryption schemes, signature schemes, and there's also symmetric ciphers. So most of the cryptanalysis on those schemes, they are scheme specific. And they also solve MQ or MP system, they are not completely random. And the goal of this work is to study the difficulty of solving a truly random MQ system and over a finite field of two elements. And the reason for that is there are a cryptographic system that is built based on MQ system over F2. And it's also possible to reduce an MP system into an MQ system by introducing extra equations. And finally, for any MQ system over the finite field of 2 to the power of n elements, you could reduce it to you could reduce it into an MQ system over the finite field of 2 elements with a mathematical trick called wire descent. So first, I will give a short introduction about the original algorithm. So this algorithm is called Crossbred. So the idea of this algorithm is that you take an input MQ system and then you compute a Macaulay matrix, which I will introduce later. And from this Macaulay matrix, you extract a subsystem which has certain special property. And because of this special property, you could apply brute force. You try all the possible assignments of n-k variables, and you could test if this system yields a solution. If not, repeat, otherwise you're done. So first, let's get to what is a Macaulay matrix. So the definition of a Macaulay matrix is just a polynomial system extended from a base system. So given a base system of n polynomials of degree d in n variables, you could define the Macaulay degree, capital D, which is the maximum degree of all the new polynomials in the extended system. So you take one polynomial from the original base system, and then you will multiply it by a monomial t, such that the maximum degree of this product is smaller or equal to the Macaulay degree. So here we have an example. So suppose this is a base system. Then if we organize the row according to the greatly reversed lexicographical order based on the multipliers, and if we order the columns according to the same monomial order, then this will be the Macaulay matrix. So you can see it's quite sparse. And after we obtain the Macaulay matrix, what we can do now is we could extract a subsystem with this property. So we would like to have a system where it becomes a linear system after we fix n-k variables in it. So here's an example. So you see, this system S, it's not linear, but if you fix the last two variables, which is x3 and x4, then it becomes a linear system. So this is a desirable property. So after we obtain this desirable subsystem, then we could start a test. We could fix variables to create a linear system from which we could easily test the solvability. So to fix variables in the extracted subsystem, the original paper proposed to use this algorithm called fast evaluation. So the basic idea is that for any polynomial, you could split it into two groups based on the variables that you would like to fix. In this example, if you want to fix the x3, then you could split it into two groups, and it's trivial that the first group, which is x1, x2 plus 1, will be the result of assigning x3 to 0. And the sum of those two groups will be the result of assigning x3 to 1. And you could apply this idea recursively to fix as many variables as you would. So like, there's some details that was not very clear to me in the original paper. The first is how do we extract a subsystem? And the second is how do we check the solvability of a linear system efficiently? So those were the like difficulty that we had to address. So first of all, how do we extract a subsystem from the Macaulay matrix? So the most simple idea is, oh, well, we could just apply Gaussian elimination. So like you could see on the right-hand side, this will be the original Macaulay matrix. But if we simply apply Gaussian elimination, the result will be on the right-hand side. And you could see like the terms that you have to keep is scattered along the horizontal line. So this is like, this will be a problem in terms of implementation, because if we store a matrix in memory, then you will have to go back to a certain point in the middle to perform operation, and this is very inefficient. So a better way is to permute the columns before you start the Gaussian elimination. So on the left-hand side is the Macaulay matrix after we permute all the columns that we would like to keep on the right-hand side. And after you finish this step, you realize that there is like a sort of diagonal structure on the left-hand side. So you could do even more than the permutation of the columns. You could even choose some rows that has exactly a desirable number of zeros, and you swap it upwards or lowards to the final position after Gaussian elimination. So the result will be on the right-hand side. As you could see, like you have almost a complete diagonal line after this operation. And finally, there's no need to perform Gaussian elimination on the whole matrix, because the goal of this stage is to extract a subsystem. And because we want to solve n variables, so this number of equations in the extracted subsystem only needs to be n plus 1. So you could see that we could ignore all the lower parts of the Macaulay matrix. We could just, after we swap the rows and columns, we could simply perform Gaussian elimination on the upper part. But like sometimes it's desirable to further reduce the size of the Macaulay matrix, and this can be accomplished by, if we go back here, on the right-hand side, if we take a row that has exactly the desirable number of zeros in the beginning, then we could perform row reduction above and below the row, and then we will come to this reduced Macaulay matrix. And from here, we could shrink it and come to the matrix at the left-hand side. As you can see, by doing that, you dramatically reduce the dimension of the Macaulay matrix, and then you could use less resources and time to compute the extracted subsystem. And as a rule of thumb, you could perform a Gauss-Jordan elimination on the original MQ system. In this way, you could see the diagonal line will be more structured, so you will be able to find more rows that has desirable number of zeros. So after we extract the subsystem, then we could start fixing variables, and this stage we could use the At this stage, we could use the graphical enumeration. So in contrast to the original algorithm proposed in the paper, we could use the graphical enumeration based on this observation. So if we have a function in the finite field of two elements, and if we are evaluating f of a and f of a prime, where a and a prime only differs by one coordinate, then we could simply take the partial derivative of the function at that point. And if we sum them up together, then we will be able to come to, then we will be able to evaluate the function f at a desirable point. And like as we will show later, like by doing so, we will be able to compute the function f at the point A in D times K machine instructions, where D is the Macaulay degree and K is the number of variables that we would like to keep. So here's an example. So suppose the function f is a linear function whose output is in x1 to x3. And you could see on the bottom there are like the relevant partial derivatives. And now if we would like to compute f at 0, 0, 0, 0, then we could first compute the result of f at 1, 0, 0, 0. And from there, you could see the points 1, 0, 0, 0, and the points that we would like to compute only differs at the first coordinate. So from there, we compute the partial derivative of f with respect to the first variable. And if we apply this trick recursively, then we will be able to compute the desirable result. So after we evaluate function f at the point, now the next question is, how do we test the solvability of a linear system? So a simple idea is that we could apply Gauss-Jordan elimination, but this is not ideal for implementation, because in Gauss-Jordan elimination, you will need to swap rows, and this can be tricky if you store the rows in registers, for example. And in that way, you will have to swap registers all the time, and this will cause machine instruction. So there's a variant, and so we propose a variant for this. So instead of storing instead of performing row, instead of swapping rows, we could keep a bit mask that tracks which row is in its final position. So initially, all the masks are set to be 1. And after a row has been finalized, then we set the bit mask for it to be 0. And in this manner, after you are done with after you finish row reduction, then you could use this mask to check if the system is solvable or not. And after we check the solvability of linear system, then we could further parallelize this process by split the search space. And you could, for example, split the search space into an equal size chunk. But this has the drawback that each sub-search space starts at different points. And this is not ideal for some computing architecture, for example, GPU. For GPU, you would like all the threads to perform the exact same operation, so this is not desirable. So like for GPU, a better way would be you could fix t variables to the subsystem, and you could create 2 to the power of t smaller subsystems. And this is better because in this way, you could start the enumeration points will be the same for each subsystem. And it's also, like one should note that like the last partial derivative of all those 2 to the power of t subsystems remain the same. So this will be the adaptation. So you first take an input and Q system, and then you compute the Macaulay matrix as the original one. And then you also then you subtract the subsystem as described it above, and then you fix t variables to create 2 to the power of t subsystems, and from there, for each of those 2 to the power of t subsystems, you fix n minus k minus t variables, and then you start testing the solvability of the after you fix variables. So for this proposed algorithm, we implement it from scratch, and we implement pure C. And in order to achieve better performance, we use Python to dynamically generate C code. And part of the program runs on CPU and part of the program on GPU. And because those two computing architecture can function at the same time, so we pipeline the process. In particular, when the CPUs compute the Macaulay matrix, the GPU will be busy in brute forcing. So in this way, you could hide whichever stage that takes last time. And we test the software with this the Sabre cluster, and it has this computing resources. And for the test batch, we use the Fukuoka NQ challenge. And the result shows that in the original Crossbred algorithm, it would take 6,200 CPU hours to solve the test case where n equals to 67. And in our implementation, it takes only about 100 GPU hours. And for larger test bench where n is equal to 74, the original algorithm would take this many CPU hours. And for our implementation, it shows that it only takes 8,200 GPU hours. And to further analyze the effect of this, we test our software with the NQ system of this particular cryptographic proposal in 2011. So its security is based on NQ system where there are 84 variables and there are 80 equations. And we show that it's possible to solve this NQ system with at most 37,000 GPU years, but on average you only need to find a solution, so the time required for that is much less, as you can see. So we also analyzed the number of operations needed to solve this NQ system, and it's a bit less than claimed. So to sum up, we adapted and we implemented the original algorithm, and the speed up can be considerable in certain cases. And we also solved both Fukuoka NQ challenges, type 1 challenges, and we also showed that it's possible to break a NQ system with this software. And its security is a bit less than claimed. And finally, we showed that like an NQ system with 80 bits of security should not be considered secure anymore. And thank you for your attention.